I'm going to start videoing the classes, so you can go back and look at what we did and what we talked about. So let's start with this one here, number 4. So first of all, part A. What advantage might students experience by teaching them to graph functions parametrically as opposed to y equals fx in a handheld? So what were your thoughts on that, Richard?
I said that it would help students see how x and y kind of vary, but on their own, so it kind of separate, and then kind of see the covariation when it's brought together.
Okay, so it's a different way of thinking about the two functions x and y together. Okay, cool.
I wrote that because I've noticed some things you can't really graph as if they're functions, and x, y is like, it seems to represent mostly just functions, so it's sometimes hard to graph something like an actual circle.
Okay.
You have to do something funky like plus, minus, crazy stuff.
Right.
So it's easier to graph, I guess, curves and stuff.
Right. No, this is an excellent point. That parametrically we can graph all kinds of curves that we can't represent as y as a function of x. Mm-hmm. Right. So it opens up this world of all these other curves that aren't necessarily functions, which is what the graphing calculator would need. Right. Strictly y as a function of x. Anything else? These are good. Great.
It helps emphasizes that when you plot a function y equals f of x, that each point on the plot is really an ordered pair of x, f of x.
Okay. Okay. You're all over it. So if not an ordered pair, what does y equals f of x emphasize? That instead of an ordered pair of two values.
Just plug something in and get something out.
Yeah, and what's the focus? What's the emphasis?
What you get out.
Yeah, the output, right? So the y equals f of x, it's like there's this focus on the y value, what you get, the output. Whereas what about the parametric equations? Yeah, so it's plotting one point at a time. You think of it at one point at a time, where x and y are kind of equals now, right? They're equals in importance, and that's what I heard you say. Yeah. Okay. Other ideas? Yeah, Michelle.
Kind of just to piggyback off that idea, I think that it is easier for students to find out which value is my x and which value is my y. I know that as a tutor, I find that people plot the points sometimes opposite of how they should be. They think that they should go their y value across the x-axis, and then they want to do something funky with their x value. So this method shows you exactly your x is this, data point, and your y is this data point. So
cool. Yeah.
Confusion is eliminated.
Okay. Other possible thoughts? Yeah, Daniel.
Well, it also opens the door to the students that there are other coordinate systems other than the Cartesian coordinate system.
Good.
Kind of gives them the aha moment, it's not so much two-dimensional.
Well, we're still in the same Cartesian plane, x and y. But what's different now? Yeah.
It could be, I want to say polar, but no, not polar coordinates.
So what's different about parametric equations in the Cartesian plane versus y as a function of x? Yeah, Matt.
You're bounded by t. T is kind of like
right.
Your manipulator in a way.
Yeah. So you have this parameter changing input value behind the scenes, right? It's not graphed, but it's behind the scenes, and your x is a function of t, and your y is a function of t. Okay. Any other thoughts on that? All right. So now I just want to part B. So on a show of hands, who figured this out? Was able to do this on your own? Okay, about a third. Okay. Part B, were you able to figure out part B? Okay, so almost half. Okay. So let's have a discussion about this. So what was the challenge in this? So was graphing g of x parametrically over -2, 3 should be easy, right? If you're allowed to change the bounds of t. So what about if we want to be set from 0 to 1? So those who are struggled or still struggling, can you talk about what your thinking is about this? So does anyone be brave and speak up with your struggle with this question.
I completely
Maria.
struggled with graphing g of x. I put it exactly how you had it,
Okay.
and it didn't graph it for me. And I asked Frank to help, and he changed x to h, and then we entered y equals g of x, and then it ended up graphing it. So it didn't
So
seem to
if
do
you
that.
put in gx, right?
And I used control 9 to do the parentheses.
Okay. There, I entered it. And click on no graph button. What's wrong?
You need to set
I
y.
put y equals g of x.
Okay. So this you did the next step also.
Yes, but it didn't do anything for me. Yeah, I didn't do that at all. Like I said, Grant had to come over and change the variable x to a different w variable just so that I could graph for us. So I don't know why it's doing that though.
Okay, so you just have a bug in your program or something like
Okay.
that. Okay. Comment.
So what I did was I did the g of x thing, but then I did a comma and I set the x bounds, and then I did another command, and that's when I did the parametric equation for the function.
So one way that we can graph that part of the, was it for -2 to 3?
Yeah.
So yeah, one way, and we learned this earlier, right? One way you can just show a part of the function, I think we did with the mortgage problem, right? Just showing one part of a function is, we can do it as y as a function of x, and then comma, and then set the bounds. Okay, so there it is. But we want to do this whole thing parametrically, right? Question? Or
No,
comment?
I just had a comment.
Please, yeah.
Oh, so when I did it, I had the x, y equals, and I also had g of x set up kind of like that, and then I don't remember what I did exactly. I just remember what I was thinking. I was thinking when t is 0, I need it to be -2 because it's between x
Okay.
equals -2 and x equals 3, right?
Okay.
So and then when t is 1, I need it to be 3, and I use that to manipulate it.
Yeah, that's now getting the parametric. This is excellent. So let's put in the parametric. Any more comments about the non-parametric version? Okay, so I gave you the command lines, right? It said control 2, and we're gonna set x, y equal to these functions of t. So x is t, is that right? And if I do y is g of t, and I graph it, so let's turn that one off. Okay, what happened? Raymond.
It only graph when t is equal to 0 to 1.
Okay, but isn't that the x-axis? That's the x-axis.
Yeah.
So why did it graph x from 0 to 1?
It's because in the function they use t as x.
Yeah, x is t, right? So we're defining x to be t. So whatever bounds we put on t, that's what's gonna get the bounds on x, right? Okay. So if we wanted to come along here, and we can easily show from -2 to 3 by just changing the bounds on t, and that will automatically change the bounds of x. Okay? But so here, here's what we want to do. We want to show this same part of the graph with the bounds from 0 to 1. Okay? So, but now we want to show the same part of the graph. So before we kind of maybe just talk a little bit, I don't want to do the whole thing, but why do we want to keep t from 0 to 1? Any ideas? What advantage is there, Carter?
If we want to use that morphing type idea that we used before,
Okay.
because then you can do the 1 minus t
Okay.
is something into the other one, because that's easier to handle that transition.
Okay. Cool. What else? Any other ideas? There's another really good reason why we want to keep t from 0 to 1. What if this wasn't the only thing we wanted to graph?
Then you would need to know how to just change the thing you wanted to change. That way they could all have different, I guess, domains.
So different domains?
Well, I don't know. Is that the right word for parametric?
Okay.
I was just thinking more of like a unit idea. So you have this unitized function in a way, like it's unitized over t, so that every single function that you're making, you don't have to manipulate each one's t bounds. You manipulate the function so that it works over t.
Okay. You hear what she's saying? So if I had an f and an h, okay, say I want to show f and h and g all on different intervals. So what if I set, but I want so g from -2 to -3 to 2 or whatever it was. And we're showing f and h simultaneously to that. See that that's problematic?
Yeah.
But if we can find a way with t from 0 to 1 to show any range we want on g, well then we can show a whole bunch. We can show f and h on any range we want on f and h as well. Okay? Alright, so I forgot your name, sorry.
Online?
Yeah. Jessica. So Jessica, say what you said before.
So, like I said, I thought how I started thinking about it is that when t is 0, I need it to be -2.
What do you need to be at -2?
Whatever x. Well, the x. It needs to be at -2.
Right.
So I have to find a way to turn t. Use something to turn it to -2. That way, it'll plot the point at x.
Okay, so what I'm hearing you say is that when t is 0, I want x to be
Yeah.
negative, was it -2?
And when t is 1, I want it
And
to
then
be
when t is 1, I want it to be.
3.
So what's the general idea of this? What's the general idea of that right there? When t is 0, I want x to be -2. When t is 1, I want x to be 3.
Is that the thing you showed us? The 1?
But what's the general idea of that right there?
Trying to find a rule that does that.
Okay, a rule. Or Yeah, function. This is the idea of a function, right? So yeah, so g of x is our function that we're graphing. But in order to do this, if we want t equals 0 to map to x equals -2 and t equals 1 to map to x equals 3, we're utilizing the idea of function. So this is the kind of thing. So function is not about having a bunch of exercises in pre-calculus. It's an incredibly powerful idea, and it's going to come up over and over and over again in this class. You have to have a function mentality when you're doing these design of these problems and like creating graphs like this. You have to think in terms of functions, right? It allows you to make a mapping is one thing it allows you to do in this case. In other cases, it allows you to process the same thing over and over and over again very quickly, rather than having to. If I want to do a process 8 times. I don't want 8 different command lines, right? I just want to define a function, and I can have it do it, all at once. So I don't have to keep retyping this process over and over again. Okay, so function is an incredibly powerful idea, and it's just going to keep coming up over and over in this course. Okay, so that's the general idea, and about half of you have figured it out. I don't want to just say it. I want the rest of you to keep thinking and working on it. How are you going to, keeping t equals to 0 and 1, how are you going to change this? This is what's graphing the function g. How are you going to change this so that keeping t from 0 to 1 graphs from x equals -2 to 3? Okay, so that is something that those of you who didn't figure it out yet still want you to keep thinking about. And so the next step in that, someone said, huh.
Well, I did it a different way before, but I just realized how to do it this way.
Okay, cool. All right, so yeah. And so if you want more help from me personally, and you know, I need to, for you as individuals, I need to kind of hear your current thinking to help you to move forward from where you're at. So I don't want to just keep going. I want to keep you guys thinking about it, and then if you need more help, I help you individually.
I just have a question about the way I did it before. If there'd be anything inherently wrong.
Okay,
that I might
we can look at it. We
Okay.
can look at it. Okay, so as an extension of this, one of your tasks for Wednesday. So you have your next critical price sheet for Wednesday, right? And you've already started because I warned you that it was longer, right? Okay, cool. So as an extension of this, I have another thing for you. Where'd it go? Down here? I guess I went down here. So I want you to look at these command lines and at your tables make sense of the command lines and what you're seeing graphed. Okay, so I want you to make sense of this is, yeah, so there's a blue curve and a purplish curve. I want you to make sense of what you're seeing there in those command lines, okay? So there are more command lines, and that's your task for Wednesday. I'm hiding them, right? So this is the setup, and then you're going to be writing 2 more command lines to produce this image. But before we can start working on that, I want you to make sense of what you're seeing in the command lines and on the graph, okay? So go, so discuss this. Or you can think about it individually for a moment, and then when you're ready to talk, you can talk about it.
The 3 numbers on the slider, that's the left, right, and they number steps, right?
Okay, yeah, so when you create a new slider, have we done it yet?
We did once.
Okay, yeah, so you define a parameter. So now defining a parameter with more than one character. Remember, you have to do the backslash, and then your string of characters, and the backslash again. And then it automatically makes that string of characters a single parameter that you can assign either a slider to or just a value. Okay, so that's what I've done here with LF, RF, LG, and RG. And then so once you have your parameter, but you could just put capital B or capital T or any open parameter. You say equals slider, and then starting value, ending value, number of steps. Starting value, ending value, number of steps. And then if you do that correctly, the actual slider pops up, and you can manipulate it with a button. Manipulate the value of what you called it. Other questions before you talk about what you're seeing here? Okay, go. So discuss with the person next to you. Make sense of what you're seeing here. And what will happen if I change one or more of the sliders? What do you think will happen?
We're seeing the graphs of X and G of X.
I'm thinking L and R stand for left.
Yeah, if you look at the one
Yeah.
side of X, it's the left, right, and there it's from -1 to 5.
Yeah.
So we
it's in the bound.
And it's so it's like
Yeah, I think if you
So it's setting the period of this.
Yeah,
So if you
it's in
move-
that.
But what's interesting is the way they're both defined, if R does mean right.
If you want a string, if you want a parameter as a string of characters. So if you just want to call a slider, say capital B, you don't need the backslashes. You just say B equals a slider. But if you want to make a string, like make a word into a single parameter, that's when you use the backslash. You do backslash, type out the word, and then backslash, and it creates. Does that make sense?
Slider for R on
Yeah,
that
what's it like?
to -2. So then they're not left or right anymore. So that switch, as if it was a negative sign function.
how come here we're using so like the L of X, like in the word.
Um, because it's describing what it is. That's part of what you're figuring out now.
Because it has a
So I chose that purposefully
Oh.
so that it has meaning.
So it has.
Yeah, so it has meaning according
Okay.
left and right bounds of what?
Okay.
Right. Yeah. Okay.
So Carter, do you switch that to this left and right? If you make it like 4 and -3,
It would have the same endpoints, but it would be
flipped over top.
Yeah.
A mirror image.
yes mirrored over the axis,
The X, right?
or
Yeah.
Okay.
well, kind of.
Danielle,
It's a little above it.
tell me one thing you figured out about this. Just
Okay.
anything that you figured out about what's going on here.
Well, the bottom one, the cosine X.
So the purple, you're saying the purple graph is cosine x. So that is f. Okay? So she's saying we're graphing f of x, and that's the purple graph. Can you say any more about that one?
Well, I still don't totally understand what this slider does, but I mean, it looks like it goes from -1 to 5 on the graph.
Okay.
Up there it's -1 and 5.
So what might the LF be referring to?
Left,
The left,
point, I don't know.
yeah, endpoint
Endpoint.
of the f function, right? And then the right endpoint of the f function. Does it agree? Do the current values of L and F agree with what you're seeing? So if I come here and I'm going to change the LF slider, I'm going to change it to -4. What will you see this column? I'm going to change LF from -1 to -4.
You just see the line expand to -1.
The
Like
line.
You would keep drawing the curve
Keep drawing the curve so that it would do what?
so that it would go to -4.
Okay. Or start at -4 maybe.
Yeah.
Okay. And then I'm going to change this one, RG. I'm going to make it, I don't know, I'm going to make it -1. Wait, so yeah, RG. What? Huh? What's happening here? So what's going on with G? So talk to me about what's, I'm confused. What's happening with G? So, Kyle.
Well, first of all, the sine function's been shifted up 1 unit,
Okay.
and it's been reflected too.
Okay. So it's shifted up and reflected horizontally or vertically?
Vertically.
Yeah. So it's flipped over its center line this way and shifted up 1. Okay. What else is going on with function G? Steven, what do you think? You notice anything else?
Well, you have the right endpoint on the left, and the left on the right.
Yeah, I'm totally confused here. I don't know what happened. Let's see. If I change this one, what's going to happen here? Oh, I just named them wrong. Did I just name them wrong?
Oh,
Well, that's supposed to be right, right?
hope so.
Okay.
Really.
I don't know how that happened.
I
So,
feel like you're messing.
what was up?
I think you might be messing with us.
No, I didn't intend to.
Okay.
Because
I-
even though you named it the
left and right, you could put them on other sides of each other because the sliders bounds can go away from each other. So what happens if you
What happens if
He
you
just
flip them?
swapped the team.
Are we okay? Is everything okay? Is it better?
What if we move to the left one? Well, the left as in the right one, positive. Well, that one.
All right, so this is a different question. Why does it show up when I put the left to the right of the right? That's a different question. So can we put that on hold?
wasn't supposed to happen.
So let's just focus on keeping left to the left and right to the right, of the other one. And then after we get this done, then maybe we can try to wrap our brains at why does it still graph something when you cross them, okay? So if you cross them, y is still getting a graph, okay. But anyway, so you got it. So that's what this does. And notice the value of t, or the range of t. 0 to 1. Okay, so I'm graphing both f and g parametrically, and I put these sliders that allow me to just manually change the endpoints of each function. And so there would be no limit to how many functions we could graph at once, and just manually set where their left bound would be and their right bound. Okay, so this is kind of an extension of that question we were just asking about, graphing parametrically, keeping t from 0 to 1. So what you're going to do is you're going to have 2 more command lines that are going to reproduce this. Two more.
For each one.
2 more command lines, right? One for each function. So you have a command line for graphing function f, you're going to have a command line for graphing function g. Okay, and so obviously the t is popped up here, so it's obviously graphing parametrically. So that's kind of an extension to this question that we were just talking about. Any questions about that? This is for Wednesday. Again, so if you figure it out and someone else hasn't, don't just give it away. Just give them the experience themselves.
So can you say it again, what we're trying to do in the next 2 command lines? Are we trying to graph the whole cosine x and 1 minus sin x, or what is it that we're wanting to do?
Making it work just like this one works. So that when you change the left hand bound of f, so first of all, I can come up here and I can change this. I can change the function, I can change the left bound, and I can change the right bound. And so you can make f and g anything you want in their lines, and then you got 4 sliders, each one controlling a bound of that function, the functions that you're graphing. So you're reproducing this same file. Does that answer the question? Cool.
Okay, so are we using similar ideas to how we did the parametric t thing we were just going over? I'm assuming
Yes, this is an extension of that question. Absolutely. So you got
I
some.
might need to look at
Yeah, sure. Yeah. So and then if you want me to look at I'm going to give you some time to work on Wednesday's homework in class. So I can come around and help you individually where you're at, okay? Because I think we have a wide range of where people are at in getting these. Any more questions about this part of Wednesday's assignment? We're good? All right, how about the 3D parametrics? How did that go? You thought it was fun?
Yeah, it was fun.
Cool. We were successful?
As far as I know, I hope so.
I don't know what it meant for a spiral to be dense at first.
What's that?
I didn't know what it meant for a spiral to be
And
dense
so then
at first.
what did you figure out?
I asked what dense meant on a spiral.
Okay. And what did you find?
That it's just basically the amount of times it revolves.
Right, so if it's more dense, it's like
Yeah.
Like it's
more squished, right?
Yeah.
More squished together, and then less dense would be more far apart. So what do you mess with here? to make it more dense. How do we mess with that? Why don't you, someone that struggled and figured it out, Bennett?
All I did was, well, since we want to do more dense, I always thought of things as a spring. So
Okay.
it's like more dense means it goes around more times
Okay.
before it goes up. So I'm like, well, I need to do something to the Z coordinate.
Okay.
That's the one that dictates how fast it rises and falls.
Nice. Okay. And so,
I mean, and since I wanted to make it more dense, I was like, well, this is probably gonna be like a reciprocal or something, like 1 over K times the 2T, or just something like that.
all right. So,
I didn't change Z.
you didn't change Z. You did something else.
I didn't change Z because to be more dense, it means I wanted to go more around in that same height. that I'm at.
Interesting. Okay.
So more spring in that same distance. So I left T alone, or Z alone.
You left Z alone. And so, and then, how did you? Okay, this is great. Okay, so how did you adjust X and Y then to make it more dense?
So to make it more dense, I was thinking, all right, like, well, cosine sine. I mean, give me the circle. So I kind of ignored that because that's the function
Okay.
itself. So I said 2 pi t, and I thought about, I'm like, well, 2 pi, my max is 2 pi, and my min is 0. Well, let's increase the max, meaning I will go around more times that same distance.
Okay.
So I put in 20 pi as my new maximum that I could have.
Okay, so
It spun around more
it spins around more, but then Z is going up at the same rate. Relative
at the
to Z.
same, yes.
Okay.
It worked.
That's why. The question is why. It's so sometimes guessing and checking is good, but we always want to ask why. Why did what worked work?
Same reason, like you
Right.
want it to just.
That's not good mathematical reasoning. Richard.
So what I did was, I know that, so if we just have cosine of 2 pi t and sine of 2 pi t, when it travels a height along this z-axis of 2,
Okay.
so when t is equal to 1, it's going to make one circular revolution.
Okay.
So what I did was I just counted the rings, I guess. I just counted how many circular revolutions it traveled,
Okay.
and I found that was like 6 1/4. So I was like, so I knew that I wanted my one revolution to go 6 1/4 times as quickly within that 2 unit with between the boundaries of 0 and 1 for t.
Okay. So you're saying you changed X and Y, or Z?
I
It wasn't following.
I just changed the frequency of what was going on inside cosine and sine.
You changed the X and Y coordinates.
Yeah.
So you like Matt, you increased the
Yeah.
coefficient.
Yeah, I think just to kind of help with Richard's argument was when we first tried to graph a circle parametrically the other day, we originally just did cosine t, sine t,
Right.
which gave us 1 radian of rotation.
Okay.
Whereas in this case, we want, and then we discovered that if we change it to sine of 2 pi t and cosine of 2 pi t, we'd get 2 pi radian rotation, which was the full circle.
Okay.
But if we want this to be more dense, we want it to have multiple full 2 pi rotations. So, or you don't even have to do end with the whole circle. But essentially, the more you change, if instead of 2 pi we had k there, whatever k is will manipulate how many rotations of the circle your spiral covers, and because of z, rather than overlapping each other on the 2-dimensional plane like it would if you did a 2D, when you've got that 3D, it spreads it upwards as it goes
Okay.
as well.
Equals 3. So let's just put it in here. Cosine. So we want to show this one, but we also want to be able to make it k times as dense. So what should I enter in here? Cosine of
2 pi k t.
2. He wants 2 pi kt. And then if we want the original one, what will we do? We want the original spiral. Rochelle wants k equal to 1.
If you want the original.
The original example or the picture?
I think it's talking about the picture is the.
Yeah, they're the same, aren't they?
Well, can't you make K a slider?
That's what we're going to do.
Alright.
So, and then what about, do we mess with z?
No.
Okay, and then someone said we want to make k a slider. So what do we want slider to be? So you say k equals slider.
0
0 to 7.
We could really make it go as high as we
Yeah.
want.
Or yeah,
Okay, so how about 0 to 5, and we'll go by 5s. So we'll just go by 1s, okay? And so if we want the original spiral, what should I set k equal to? And let's see if this works. Is that it? Then why not the picture that they gave
I
us?
think the picture that you gave us is like the one that's more dense.
Oh, it is more dense. Okay.
Yeah, because you said replicate something that looks like this.
So so this is something I learned years after doing all kinds of three-dimensional graphs. If you hit Control and then grab the axis and slide in the axis, you can just easily increase the side.
Every time I touch that axis, the thing just started spinning out of
Right.
control.
So if you hit Control, you can adjust it to get it how you want. All right. So I think it'd be cooler if we do like say by 100. There's one. There's one. Okay. So as I increase k, yeah, we need to go higher. Yeah, there's a commercial. That looks like spaghetti. See the commercial before?
I've never seen that.
It's the football players. It's like a charity for football, like some football players taking kids around in the museum.
yeah.
He says something really profound about the picture, and the kid goes, "That looks like spaghetti." What do you think? Where is that? There we go. So you can spin it. Okay, what about the next one? How did you make it appear, the spiral appear the size of a cone? Somebody new. Victoria, did you have success on this? To make the cone number 6? You did?
Mhm.
What'd you do?
I put a 6 in front of the cosine and the sine.
You put a
To make it,
like this?
yeah.
And why? Why? Why does that work? Make a cone. Sure.
I was gonna say that I noticed that as I put a coefficient in front of the sine or the cosine, the circle, as long as it's the same one, it would be the same. It would get bigger and smaller. So I figured if I put a t in front of it, it would grow with the t. Wait,
Yeah.
You hear what she said?
I need a T of 6.
So you're both saying you want the coefficient of t on there. And so why does this work?
So it's gonna start out at RT is at 0, so it's gonna have a radius of 0.
Radius of 0.
As the t gets bigger, then it'll expand out to t. But
Okay.
it's gonna only go to 1 again.
So let's put k back at 1 here. Or something close to it. All right, and well, but you can't really see it, so they work. Okay, cool. Now, what about now you want to use n to animate and have this thing smash up and down? Somebody new. Steven, did you get this?
Yeah, well, kind of, but I think all you have to do is put n for z. Then that's gonna change.
Instead of 2t, you just want to take the 2t out and make it n.
Don't make it nt,
nt. So tell me why.
because you want to change the height depending on what t value you're
So then it's going to go up to 10.
Okay. What do you think about his reasoning? Anna, did you get this one?
Oh, that's what I think.
That's what you did. Yeah,
I was
Rochelle.
kind of thinking how Carter talked about it. If you have a 2D plane and you're having cosine and sine map out several revolutions, you
Okay.
don't actually see that. You don't see it in 2D because it's all flat and it just traces along itself.
Okay.
So, if the spiral was flatter, if you're looking at it straight from above, it would look like, it'd be like a galaxy or like a universe kind of spiral. So as we stretch the z, as we pull it out, we're gonna expand and make the spiral come out of the paper essentially, or become 2-dimensional or 3-dimensional. Yep. And if you go all the way down to 0, then you have that. That's what it looks like in 2D on our XY. Or looking at it.
What if I look right down on the z-axis
Ooh.
and then I change n? Richard.
If you're looking, are you talking about like you're straight above?
Yep, straight above. So I can
It's
manipulate
gonna
this.
look all the same.
Why?
Because the x and y distance of the spiral is the same no matter what. We're just kind of stretching it upward. So they're just, all those points making up the spiral are just going higher along the z-axis. But their x and y distances aren't changing at all.
It's gonna be hard to get it
Yeah.
to know.
Perspective.
Yeah, it's hard to know where I'm looking right down the axis.
That looks pretty good.
It's gonna hypnotize all of us.
Well, it's because of the camera. It's the depth perception.
Yeah. So so the idea would be that if we were looking straight down that z-axis and you changed n, you wouldn't see anything any different because you can't see n is only affecting z. N only affects z. Okay, how about the last one? The inequality. Somebody new.
You just gave a big hint towards it.
What's that?
You just gave a big hint for it.
I did?
Yeah. You called it inequality.
Oh. Well, hopefully you figured that out.
Kept trying to do it parametrically because the whole thing.
Okay. Then you come to a point of abandoning and trying something
You
else?
have the line to sweep that area, but just not close it in.
How many people were able to get this on their own? Most. Okay, good. So let's see who is. Danielle, tell me what was your process?
First, I noticed that it's sort of the area between two linear functions.
Good. Okay.
So I kind of figured those out based off of the few points that we had to work with.
Right.
And then like where they intersect, and then I looked at which function was below and which function was above the
Okay.
area, and then I just did the below function is less than y is less than the function that's above.
Very good. Okay. So what did you find? Do you remember what you found?
It was 3x minus 3.
3x minus 3
Is less than y
is less than y.
is less than negative 0.5x plus 1.
Okay. So why does this give a solid block of color? Can explain why does this give a solid block of color? Julia, you've been quiet today. Or will it? Maybe, so this is what she's offering. Will it give a solid block of color, and why?
I said it was less than or equal to.
Okay. How will that? So fair enough. So I'll just. Jeez.
Yeah, it doesn't like to do that.
It's weird how it throws things at the end. But anyway, so
Yeah, I thought of it like she did. I saw two lines.
okay,
They intersect at one point.
right.
And I want all the solutions that are in that purple area. So I set up just like she did.
Okay, so it's all. So what is it graphing? When you look at this, what should you see? What is your image of what you're seeing there?
I was just gonna say it's everything greater than the line 3x minus 3. And
You
then
see
plus the
everything. What? So what's everything? Every what?
all of the
points, right? So this is, you got to see this as a points. This is all points. What that satisfy? That's all y values. Let's see. Above, this is 3x minus 3. So everything above, right? That, because y is up and down, and everything below this one. So it should look just the same here if we did it right.
I was frustrated trying to figure out what the equation of the lines were.
That's kind of sad, Trevor.
Just without actual points being labeled, I was just like, bothered me.
That's pretty easy. Okay. All right. So another also for Wednesday.
Oh. Oh. Oh, that
4 lines and no commas. Fun.
4 lines, no commas.
You flying a kite at the
Yeah,
park?
4
What's going on here?
Yes, I'm flying a kite at the park.
with a hole in it.
Oh, we're still not circular here. Oh, right. I figured out how to do that. Go down to the next 60 hertz. I think that's the one I did. Do we have a circular sun? Much better. Much better. Okay, so that's one of your tasks. It's 4 command lines to do that. Yes, ma'am.
Post this on Blackboard.
Yeah, they're both, everything's posted on Blackboard
When did you post it?
before class.
Okay.
What?
Because I would have done it over the weekend.
Is it for this one?
Yes, for this one.
This one.
Okay, and then
Oh, wow.
1 command line.
Oh, what?
1 command line in GC. Okay, so you've got plenty of work, and so I wanted to get you